Greetings and salutations, magical chemists. Let's talk about electrochemistry, which is the study of redox reactions that produce or require an electric current. Most of our unit is going to be studying electrochemical cells. This is where chemical potential energy transforms into electrical energy, or vice versa. Basically, this is a fancy way of talking about a chemical reaction that involves the transfer of electrons, otherwise known as redox. There are two different types of electrochemical cells we'll be studying. The first one is called a voltaic or a galvanic cell. This is what happens when you have a spontaneous redox reaction, and it can be used to produce an electric current. The opposite of a voltaic cell is an electrolytic cell. This type of cell is non-spontaneous. It will only undergo redox if you make it by applying an electrical current. Let's go ahead and remind ourselves what's happening in an oxidation-reduction reaction, aka redox. Basically, it's where electrons are being transferred from one atom to another. If a substance accepts an electron, we say it's reduced. But if a substance loses an electron, it's oxidized. It's important to note that electrons will always be transferred from the species that is oxidized, the ones that lost the electrons, to the species being reduced, the ones that gained. Now let's take a look at how we can determine who's being oxidized or reduced in a given chemical reaction. Of course, the key is looking at the change in oxidation state. A substance that has been oxidized or lost electrons will have an oxidation number that becomes more positive or less negative. A substance that has been reduced or gained electrons will have an oxidation number that becomes more negative. To really focus on oxidation and reduction, you can actually split a redox reaction into two separate half reactions. The oxidation half reaction will show electrons as a product. For example, down below, we're showing zinc being oxidized. Well, if we show a zinc 2+ ion and then the loss of 2 electrons. That's why the electrons are products in an oxidation half reaction. The reduction half reaction, therefore, will have the electrons as a reactant. I use the alliteration to help me remember. The reduction half reaction has electrons as a reactant. And if you look at the example half reaction down below, you show iron 2+ gaining 2 electrons and thus being reduced. Notice the change in oxidation state. The iron 2+ ion has an oxidation state of +2, and look, its oxidation number is literally reduced. It goes down to 0 when it gains those 2 electrons. Whereas zinc, being oxidized, shows a more positive oxidation state once it lost electrons, which hopefully makes sense. You can actually quantify how likely a particular chemical species is to be oxidized or reduced. So let's take a look at reduction potential values. This is just a quantitative measure of the tendency of a chemical species to gain electrons, aka be reduced. Reduction potentials are measured in volts or sometimes millivolts. And all reduction potential values are measured relative to the potential of H+ to gain an electron. To read a reduction potential chart, it's important to remember that the more positive your reduction potential, the more likely it is for that species to be reduced. Basically, the more positive, the more it wants electrons. The more negative your reduction potential, the less likely it is to be reduced. So here is a classic standard reduction potential table. Notice right about the middle here, good old hydrogen being reduced. And we have set that value to 0 volts. So that is our relative standard. Anything more likely to be reduced than hydrogen gets a positive potential. Anything less likely gets a negative reduction potential. And don't worry, these tables are definitely not something you have to memorize. You will be given whatever information you need, the standard reduction potentials needed to solve any given problem. Now, it's important to note that if you have something like your cobalt 3+ ion with a very high potential to be reduced, that means it's much less likely, its product is much less likely to be oxidized. If cobalt 3+ will do anything to steal the electron, cobalt 2+ doesn't want to give it back. Okay, so that's a standard reduction potential table. Let's see what we can do with it. One thing you can do is predict if you're given two species to compare, which substance will be reduced when those two species are put together? Basically, whatever has a greater, more positive reduction potential is the one that'll be reduced. The one with a smaller or more negative reduction potential, that one is going to get oxidized. Now, we've only been talking about reduction potentials, but there are oxidation potentials as well. And it's very convenient. If you switch the sign on the reduction potential, that gives you the oxidation potential. Let's take a look at a quick example. Using our standard reduction potential table, I can see that the reduction potential for the cobalt 3 plus ion is 1.92 volts. Well, if you flip the reaction, you have an oxidation half reaction. And since cobalt 3 plus has a really high reduction potential, right, very positive, it really wants that electron, that means it's very unlikely that it's going to give it up. It's going to have a very low or very negative oxidation potential. And it's exactly the same value, but with a negative sign. That means on AP Chem tests, they won't usually give you a table of oxidation potentials. They almost always just give you reduction potentials. And you're expected to know, well, if I need the oxidation table, I just flip it. Please note, a lot of times these reduction potential tables are not labeled as E red for reduction. However, you're expected to look at this table and see, hey, electrons are reactants. This is reduction. So the fact that this is a reduction potential is implied. All right, let's go ahead and try a couple of example problems to see what kind of questions they might ask you. Okay, here are two beautiful problems that you can totally go ahead and try. The first question wants to know if the reaction given, is it a redox reaction? And if it is, identify what was oxidized and reduced. And the second one just wants you to rank. It gives you four metals, four solid metals, not their ions, and it wants you to rank them in terms of most easily oxidized to least easily oxidized. All right, you are going to try both of these beautiful problems. And when you are ready to check your answers, go ahead and unpause the video. Okay, for the first one, if you want to know if something's redox, you have to check the oxidation states of each individual element and see if they change. Well, your two reactants are both neutral elements, so they both start off with an oxidation state of 0. And then your product is an ionic compound, which makes the oxidation states easy because they match what you would predict their ionic charge to be. So aluminum has an oxidation state of +3 in aluminum oxide, and oxygen has an oxidation state of -2. So now, hopefully you can tell, well, the oxidation state's definitely changed. Heck yeah, it's redox. Now this question uses the verb identify. That means you don't have to justify your answers. You just have to identify. But we're going to go ahead and justify just to make sure you can understand why. So hopefully you can tell that aluminum is being oxidized. There are two ways to tell. The classic way is to say, well, its oxidation state got more positive. It must have lost electrons. But did you notice? Aluminum was by itself. And then who did it get attacked by? Oh yeah, oxygen. It literally got oxidized by oxygen. So this is a really nice shortcut to notice. If you see a chemical reaction where you have something that wasn't with oxygen, and then at the end it is with oxygen, it usually, most of the time, totally got oxidized. That's where the name comes from, because oxygen is so good at oxidizing things. Okay, which means, of course, that since oxygen was the thing that did the oxidizing to aluminum, oxygen itself got reduced. I mean, its oxidation state literally got reduced. It went down. It went from 0 to negative. So there's a couple of different ways to answer this question, but notice, if you only had to identify it, you could use whatever method you want, whatever is fastest. Please note, when they ask you to identify what's oxidized or reduced, your answer will always be one of the reactants. Okay, for the second one, it says rank in order of most easily oxidized to least easily oxidized. And you're looking at copper, nickel, silver, and lead. Well, this is where we totally need to check out that table of reduction potentials. Once you find them on the table, you'll notice that silver's at the top and nickel's at the bottom. But remember, these are reduction potentials. So since silver is most easily reduced, that makes it least easily oxidized. And if you want to do it numerically, you could just write the oxidation potential values. So numerically, you can tell the greatest oxidation potential is nickel and the lowest is silver. Okay, let's try one more type of practice problem. There's a couple moving parts going on these. So notice that we've given you a complete reaction, and we're saying write the half reaction for each of the following, I guess it should be half reactions, for each of the following redox reactions, and identify what's being reduced and oxidized, and write the correct reduction or oxidation potential. Yikes. So we're going to do one together, and then you're going to try one on your own. First things first, oxidation states. Luckily, these are really straightforward because you have just ions and elements. Once you've identified the oxidation states, you have to figure out which one got oxidized and which one got reduced. Since nobody got attacked by oxygen, we have to go by the numbers. Zinc got oxidized because it lost electrons, and cadmium stole them. It gained the electrons, so cadmium got reduced. What a cad. Now we're going to break the reaction apart and separate it so we have a half reaction for oxidation and a half reaction for reduction. First, you start off with just the ion and element as a reactant and a product. Lonely, sad tears. I just realized I did all my colors backwards. There we go. Now we can write our half reactions. But if you're writing half reactions, you also have to include electrons. There are two ways to figure out where the electrons go. You could just remember, oh yeah, reduction has electrons as a reactant. How many electrons? Well, look at the change in oxidation state. It went from 2 plus to 0. It gained 2 electrons. But you can also do this by balancing charge. The charge on both sides of the reactions has to be equal. So the charge on this side of your half reaction is 0. The charge on this side is plus 2. So to make sure they're equal, the electrons would have to go on the product side. Now the charge on both sides is 0. And that's how you know the electrons are on the right side, or the correct side of your half reaction. Okay, we're almost done. We just need to write the correct reduction or oxidation potential next to each half reaction. This is just an exercise in looking things up in that table. So take a moment, if you haven't already, to try to find those values. And when you're ready to check, unpause the video. Did you find them? The most common mistake is forgetting to flip the sign when you're writing the oxidation potential. So watch out for that one. All right, there's a second one to try, and you guessed it, you're gonna try it. So go ahead, do all the same steps we just did in number 3 on number 4, and when you're ready to check all the beautiful parts, go ahead and unpause the video to check your work. Hopefully you started with oxidation states, and you used the oxidation states to break them apart into half reactions, making sure to include electrons in the half reactions. Once you have those, then you just look up the numerical values of the potentials on the table. And there you have it. Hopefully the world of oxidation and reduction is starting to make a little more sense. One quick thing to point out before you escape. Notice the coefficients of 2 on silver. They were there to balance the equation, more about that to come, but notice you did not need them in the reduction half reaction, because otherwise you would have had a coefficient of 2, 2, and 2, and guess what? Those all cancel. So that's why in the reduction half reaction, we only show the 1 silver ion gaining 1 electron going to 1 silver atom. All right, I hope that was as shockingly awesome as you thought it might be. Thank you for playing with the glories of chemistry.